it's me again. In this lecture, we're going to look at transcritical bifurcations. In the previous lecture, we had looked at saddle node bifurcations. So in this lecture, we'll start off with the transcritical bifurcation discussion, and then we'll move on to pitchfork bifurcation. So in the previous lecture, we've already looked at the normal form of a saddle node bifurcation. The normal form for a saddle node bifurcation was of the form r minus x square. X dot is equal to this. So a transcritical bifurcation is quantified, or rather is characterized by a form r dot equal to rx minus x square. Let us have a look at how the plot looks like. But before that, let me copy the usual snippet. Okay, so let x be np dot linspace minus 2 to 2. Let us define a function show transcript. Let r be the input to the function, and we'll do a plot x comma r times x minus x square, and let us call the widget. So w equal to interactive show transcript r equal to -1 to 1 in steps of 0.1. All right, and lastly we have to show the widget as well. So this is the plot. Let us additionally plot the x-axis. So plt dot a x h line and 0. So this plots a horizontal line. Let us set the color of the line to black. All right. So when r equal to 0, obviously this particular equation boils down to x dot equal to minus x square, which is a parabola facing downwards, and there is exactly one root, that is this x equal to 0 is the fixed point. Okay, and that is a half stable point. Whereas when r becomes negative, we have the occurrence of two roots, and when r becomes positive, we again have occurrence of two roots. So unlike the saddle node bifurcation, where changing r, it led to two conditions. It led to a sudden appearance of roots. Okay, so essentially we had a parabola which did not intersect, and when we changed the parameter, we had an intersection. So no roots, no fixed points, fixed points. But in this case, there seems to be a common root, and obviously the common root is x equal to 0. So we can write this as x dot is equal to x times r minus x and the roots of this. So the fixed points are positions where x dot is equal to 0, and it is 0 at x equal to 0 and x equal to r. So obviously when r is negative, we have the other root appearing at negative values. Let me also plot the vertical line. Okay, so that's the vertical line. So you see one root is always 0, while the other root simply shifts around. Okay, so what is actually happening? We have basically these conditions. One is this. So in this particular case, what is the stability of this point? So we have seen in the previous lecture that the stability of a fixed point depends on the slope of the function at that fixed point. Slope over here is negative, so this point is stable. So the flow of points on this line will be towards this point and towards this point. And it is obvious if you do the whole reasoning with an initial condition somewhere and how the point travels on the line. So x dot, so this is x dot, so and this is x. So if the initial condition is over here, the particle has a negative velocity and it moves towards this point. Over here, the particle has a positive velocity and it moves towards the right. Okay, so 0, or rather the fixed point x star equal to 0 is stable. So this is the condition for r less than 0. What about the condition for r equal to 0? Okay, so at r equal to 0, the slope is equal to 0 and this is a half stable point. But what about r greater than 0? So this is the fixed point, but the slope over here is positive, and that implies that this particular fixed point, that is x star equal to 0, it becomes unstable. So if we draw this particular curve, if we draw r on this axis and x star on this axis, so we know already the roots are x equal to 0 and x equal to r. Okay, so let me mark the x equal to 0 root with the magenta line. So this particular line are the fixed shows the fixed points x star equal to 0, while this particular line is x star equal to r. So in the plot x star versus r, this will be the line. But when r is less than 0, we see that the origin, rather the x star equal to 0 line, is stable. So this is stable. But once it crosses r equal to 0, this branch becomes unstable. Now similar reasoning, we can see that when x star is stable, x star equal to 0 is stable, this other root, that is x star equal to r, is unstable because the slope over here is positive. So this is unstable. Whereas over here, the other root, x star equal to r, it becomes stable because the slope over here is negative. So this is unstable and this becomes stable. So essentially we have two roots or two fixed points, and the changing parameter r leads to an exchange of stabilities of the two roots. So in a physical problem, if we have the condition where the changing of a parameter leads to that same fixed point, it still has the same fixed point. Okay, we are not changing the number of fixed points, it still has the same fixed point, but the nature of the fixed point changes as we cross. Okay, such a kind of bifurcation is called as transcritical bifurcation. All right, so let us make use of the code that we had in the previous lecture. We can make use of this, we can reuse this code that we had written in the previous lecture, and instead of the saddle node normal form, we will now use the transcritical normal form, that is r times x minus x square, and the slope will be r minus 2 times x. All right, everything else remains the same, and the title of the plot will be transcritical bifurcation. So let's run this program and see what happens. Okay, so we do see, so see the filled markers were stable points, while the cross markers were the unstable points. Let me suppress this. Okay, so one little thing I want to just get out of the way. In Python, you don't really need to put semicolons at the end of an expression or a statement. Okay, unlike Octave, where you want to suppress output, you have to put a semicolon. But in doing stuff on Jupyter Lab, if I do not suppress this, I will get that annoying text. So I want to suppress that, so I put a semicolon, and it's an old habit I have from using Octave or MATLAB. Okay, it makes no difference if I put a semicolon over here or not. Okay, I can remove all the semicolons, everything still is the same. But semicolons do help if I want to put multiple expressions on the same line. Okay, I can put multiple expressions over here on the same line, and I can separate them by a semicolon. It does, but if I remove this, then there will be an error. It tries to interpret the entire line as a single executable statement. Okay, so that's something I just wanted to get out of the way. So over here we had a stable branch which became unstable. We had a unstable branch which became stable. So this is an example of a transcritical bifurcation. So now let us go to a very simple problem, and that problem is to find out the bifurcation diagram or the bifurcation space for x dot. So let me copy the question. X1 minus x square minus a times 1 minus e to the power minus bx. So this is the question. So by specifying the bifurcation space, it means there is a certain combination of a and b. So if I plot b on this axis and a on this axis, so there's a certain combination of a and b for which this particular vector flow, okay, this is also called as a vector flow, it will show transcritical bifurcation. But whether or not it's a region in the AB space, so we are not working in the x prime space anymore. We are trying to analyze this equation in the abstract space AB. So it's a parameter space. Okay. So in the AB space, what is the zone or curve or whatever it is which causes this equation to exhibit transcritical bifurcation? So straight off the bat, we can say that x prime, so the fixed point of this particular equation, fixed point where x dot equal to 0 corresponds to x equal to 0. If you substitute x equal to 0, we see that this entire thing becomes 0 and this becomes 1, so 1 minus 1 is 0. So x equal to 0 is a fixed point. Now what we want to know is whether it exhibits transcritical bifurcation. So when does, mathematically, how can we say whether a certain point, say this fixed point x equal to 0, whether that point has some transcritical bifurcation going on? So over here we had x equal to 0, and we could say that there is a transcritical bifurcation because in changing the parameter there was a change in the slope of this entire curve at this point. So if we can find out the parameter space a and b for which this particular fixed point changes slope, then we can say that yes, that equation does show a transcritical bifurcation. But even before that, we can sort of fix A and vary B to see what goes on. Okay, let me copy this. Let me paste this. Let me give this cell some context. So this is not x equal to x 1 minus x square minus A 1 minus exponential of minus bx. So we are trying to, so this has to be interpreted as markdown. Okay, so we are trying to solve this equation, rather trying to find out the properties of this equation, if you like. So let me change this. So this has to be x times 1 minus x square minus, so now let me fix a. So let a be equal to 1. Okay, and this will be 1 minus np dot exponential of minus b times x. So let b be represented by r, because we are already passing r as a input to the function. So let b be representative of r, rather r be representative of b. So the derivative over here will be 1 minus 3 times x square, and there will be, so the derivative will be minus r times np dot exponential of minus x. Okay, so r is varying from minus 2 to 2, that's fine. Okay, so essentially this will be the plot where a is equal to 1. All right, so let us run this cell and see what happens. Okay, so obviously we are, okay, so we are missing a few roots over here, and the reason is, okay, so the reason is clear. We are not passing enough guess points. So why is it important to pass enough guess points? Let me show you. Let me first plot this. So let x be np dot linspace minus 3 to 3. Let a be equal to 1, and let us pass everything into a function. So def show fun, and let the input be r. Let us put all of this inside the function, and let f be equal to x times 1 minus x square minus a times 1 minus np dot exp minus r times x. plt dot plot x comma f. Let us put it in an interactive widget. All right, we have to show the widget also. Let me show the x-axis as well. Let me make it black, and let me set the y-lim minus 1 to 1. That's fine. Oops, there seems to be an error. Let's see what the error is. So color equal to minus k. Okay. Oops, there is still some error. What is the error? We cannot give line style. Okay, so it has to be only k. Fine. So let us see what happens. Okay, so we have the presence of 3 roots, but over here we were passing only 2 guess points. So when we are passing the guess point minus 2 and plus 2, it is converging to this root over here and this root over here, and we are not able to capture this root. So let me pass an additional guess point of 0. Okay, so now let me rerun this cell. Voila, we do have the 0 root. So watch closely what happens. We have the 0 branch, and suddenly it loses its stability. So it's rather it gains stability. So it's unstable up until this point, and then it becomes stable. So obviously there is a transcritical bifurcation occurring for the root x equal to 0 at b equal to 1. Okay, but we are more interested in probing this entire parameter space. For what parameter space does this happen? So let's have a look. Let us take this entire code. So the beauty about doing this in Jupyter Lab is we can reuse all the snippets that we have already done, okay, rather than having to write everything all over again. Okay, so let us pass A as well. We need to eventually pass A, and this will be A times this, and this will be this. In fact, let me make it B so that we maintain the sanctity of this problem. And this will be B. This should be P times X. So obviously there was an error over here. This should be R times X. Okay, let me run this. Okay, no harm done. Great. So avoid doing such errors. I'm strapped for time, so I'm trying to go through the code as quick as possible. Okay, so let me define A as np.linspace. We don't need X array over here. I don't know why we've kept this. Let B be np.linspace minus 2 to 2. So far we have defined the parameter space A and B. This has to be B. Let me make a two-dimensional space AB. So if you recall, we can use mesh grid to declare two arrays like this and to form an entire grid from these two arrays. Okay, so A and B will contain all the grid values of A and B. All right, so for R in RA, this should be, in fact, let us do this. For I in np.arange 0 to np.size of A. For j in np.arange 0 to np.size of B. So whatever A and B you declare, depending on that size, I will loop over all the different values of A and J will loop over all the different values of B. Okay, so essentially this is a double loop. I mean, there are techniques where you can avoid using a double loop, but in order to keep the code readable at this stage, if you are not comfortable with those tips and tricks, I'm keeping it as readable as possible. So we have to pass to fsolve the two parameters. We have to pass A and B as two parameters to the function. Okay, if the solution is converged, then what should we do? If the solution is converged, we must look into the roots. Okay, so instead of looping over all the roots, checking the stability, we are more interested in the x equal to 0 root. Okay, so how do we extract the x equal to 0 root? That is the question. Let us see what sol contains. So sol contains these things. So sol 0, it contains all the roots. So we must find which index contains the root. So in general, these won't be 0. There will be 3 different values, but one of those values will be close to 0. This is what we expect. So because we are probing the change of stability of the x equal to 0 branch, so now we have to extract the x equal to 0 root. So how do we do that? So roots equal to sol 0. We have extracted all the roots in. So forget about all this. We don't need all this one. So now all the roots are dumped into the variable roots. Now let me say 0 root. So 0 root has to be that root inside roots which is close to 0. And I say close to 0 because when the computer uses a non-linear algebraic solver, it will return roots which are not exactly 0. It will return roots which are 10 to the power minus 9, 10 to the power minus 6 or something like that. So 0 root, we have to check for something which is inside roots and it is something close to 0. Okay, so how do we do that? We will say, so np dot is close roots comma 0. So this particular statement, and let us give an atol of 1e minus 8. So this particular statement will say out of these roots which one is closest to 0. So now we have to extract that root. So this will be roots of this, which will satisfy the condition this is equal to true. And we have to give the index. So np dot where this condition holds true. In fact, let me demonstrate this. Let me define a variable c. So let it be minus 1, 1e minus 7, and 1. Okay, so this is c. So now let me say np dot is close c comma 0 comma 8 all equal to 1e minus 6. So it says false, true, false. So I must extract this index of c. So I say this is equal to true, and I say np dot where. So it says the array index is 1. So I must extract that. So because the output of np dot where is inside a tuple, I must extract that value. So it has to be 0, 0. And this gives me the array index. So this gives me an idea that I have to write it like this. Okay, so where is the np dot where it is equal to 0, and I must extract the tuple. So these are some idiosyncrasies of Python where you have to extract the value of the tuple. Meaning, if I remove these zeros and I print this, so it says it returns array 1 d type data type. So if I say just 0, it will give array index data type, and if I extract this, it will give me 1. If I extract this, it will give me the okay, it's out of bounds. If I extract this, what do I get? Nothing. So the tuple is out of bound, but in order to extract the index, this particular index, we have to do this fancy thing. Okay, so this should give us the 0 root. Now after finding the 0 root, what should we do? We should check for the slope at that point. So slope at 0 root equal to, so df dx, so df dx x comma ai comma bj. So this has to be ai comma bj. All right, so now we have the slope at the root, but we are more interested in the sign of the slope of the root. So let us say sign of the slope of the root, and we will call the np dot sign function. So if the sign of something is less than is negative, np dot sign will return -1. If the sign of the slope is 0, it will give you 0. If it is positive, it will give you 1. Okay, so now we have extracted the sign of the slope, and we must now dump this value -1, 0, or 1 into an empty matrix. So let's see the np dot zeros, np dot shape of a. All right, so we have initialized c as 0, and cj comma I will take the value of sign slope 0 root. So it's j comma I, and the reason is, look over here, ai is this and bj is this, but I is actually the column number, j is the row number, and I is the column number. Okay, so that's something you need to keep in mind. Alright, so this gets the value. Once everything is done, we should do a p color plot, a pseudo color plot. So plt dot p color a comma b comma c, set aspect 1, we don't need these things, and we'll select the title later on. So the title should be bifurcation space. Alright, so let's run this cell and see what happens. Expected and okay, so we forgot to indent everything in the for loop. Now everything is inside the double for loop. Okay, there's an error. So the error is because we are passing x. We should not pass x. We have to pass the value of the zero root. So this has to be zero root. So essentially what we're doing is we're finding the zero root, we're taking that value, and we pass the zero root to the function which finds us the slope at that point. Okay, and this is that function. So instead of passing x, we should pass zero root. Okay, so with that small error out of the way, let us run this and see what happens. Let me suppress the printing. One little thing before we continue, in order to avoid some spurious things happening, let us give fsolve an initial guess of 0 rather than something which has a range. Okay, so this will help us to isolate things better. I don't care about the other roots. All I'm worried about is the x equal to 0 root. Okay, so let me run this and see what happens. Okay, so the bifurcation space, it shows that in the yellow region, so let me put a color bar. So the slope over here is positive, the slope in this zone is negative. So when it crosses this curve, we have a transcritical bifurcation at the fixed point x equal to 0. So this is the zone where the transcritical bifurcation occurs. Let us quickly look at what that curve actually is. It looks something oddly specific. And is there a theoretical way we can figure out what that bifurcation curve should be? So it's obviously a curve. It's a curve which looks like this, and it's a curve which looks like this. But what is it really? Let us look at it. So x dot is this. It means that x dot in the vicinity of small x, it will be x times 1 minus x square minus, so when x is small, rather bx is small, when the argument bx is small, we can use a Taylor series expansion to write this 1 minus bx plus b square x square by 2 factorial and so on. And we can simplify this as x minus x cube minus a times, so 1 cancels out, this is bx minus b square x square by 2 plus higher order terms. So what does this become? This becomes x times 1 minus ab plus ab square by 2 times x square. So what is the fixed point? So the fixed point is x times 1 minus ab plus ab square by 2 times x. So one fixed point is obviously x equal to 0, and the other fixed point is obviously this root. So this root will be x equal to twice of ab minus 1 upon ab square. So when you set this inside thing to 0, this is the other root that you get. So these are the two roots. And what is df dx for this entire thing? Df dx in the vicinity of x, okay, in the vicinity of x, I mean, this is not the correct way of writing it. So df dx in the vicinity of x is equal to 1 minus ab plus ab square x. So when we find out the slope at the fixed point, we set this to be 0. So this becomes 1 minus ab. So the slope 1 minus AB, when it is 0, it implies AB equal to 1. And AB equal to 1 is a rectangular hyperbola which looks something like this. And that is exactly what we see over here. So that is the demarcation, that is the bifurcation curve in the abstract AB space. Okay. So when 1 minus AB is greater than 0, what happens? This zone, this is that zone where we lie. When 1 minus AB is less than 0, this is the zone that we lie. And hence this is the boundary which separates the two zones where the slope changes for the fixed point x equal to 0. And that is the description, that is the mathematical description of the curve in the bifurcation space. Okay, so let us conclude this over here. In the next lecture we'll look at pitchfork bifurcations. So far in this lecture we have looked at how a fixed point can change its stability when a parameter is changed. Okay, and it is different from a saddle node bifurcation in the sense that no roots are created or destroyed. We are focusing on one fixed point and how it exchanges stability. We have looked at a problem in which we've studied the bifurcation space description of the same problem and how we can numerically plot the bifurcation curve. Okay, so with this we end this particular lecture. I'll see you again next time with a lecture on pitchfork bifurcations. Until then, it's goodbye.